Thank you very much, Michael, and thank you for the introduction and the invitation to be here. It's my pleasure to present my most recent research with you all. Oh, great. Okay, so first I want to just familiarize everyone with UT Dallas. So we're in North Dallas, particularly, and so we have a sister institution called the UT Southwestern Medical Center, which is downtown Dallas. And so I personally collaborate quite a lot with the prosthetics program there, which is directed by Gregg, who has contributed to a lot of the work that you'll see. And also I want to point out, because not many people know this, that UT Dallas, we are the Comets. And try to remember that because it'll come up later when we start naming some of our robots, okay? So the main challenge that I want to share with you today, it relates to amputee locomotion, but some of these things are also shared by patients who have had a stroke. And so in particular, lower limb amputees tend to walk slower. They tend to spend more metabolic energy walking because they have to compensate with their residual intact limbs for the lack of energy contributed by the prosthesis. And they tend to fall more frequently because the prosthesis is not actively responding to perturbations or disturbances. So it's akin to walking on stilts, right? So it's not an easy thing to do. And so one of the approaches that we have been pursuing as a community is to introduce robotics into the prosthetic devices. And in particular, when you're adding sensors and actuators, you then have a control problem in the middle, right? So how do you synchronize these powered devices to the intended motion of the user so that they can walk as they want to walk as opposed to walk as, say, the robot would like to walk, right? Because in this application, the tolerance for autonomy of the robot is fairly limited, okay? So this is the state-of-the-art control approach that we often see in the literature for wearable robots. So we typically look at the Gait Cycle and we divide it up into a sequence of phases that are represented through this finite state machine, and each phase has its own control policy in there. So typically there'll be a PD controller. So, and every single one of these phases has a PD gain and a set point. And then there are also switching rules between each of these phases, which determine the transitions, and of course, those are incredibly important to synchronizing the behavior of the prosthesis with the human user. We also will see a higher level state machine that provides the essentially the intent of the human in terms of whether they're walking upstairs or climbing downstairs or level ground. However, these tasks are limited to a discrete set, a small discrete set, which are then classified by some machine learning algorithm. Now, the problems with this discrete approach is that it's, first of all, not continuously synchronized with the human user. These switches happen discretely, and once you've moved forward, you usually can't move backwards. So if the prosthesis mistakenly switches phases early, then there's no going back. And if the person was to stop on a dime and want to walk backwards suddenly, which can happen, the prosthesis can't do that. So, and additionally, we see with the tasks that you cannot perform any task in between these discrete options, right? So there's no continuous synchrony with the user. And perhaps more important to the clinical viability of these devices is the explosion in the parameter space. So we see hundreds of control parameters for these hierarchical state machines that are user dependent. So the parameters that work for me won't work for you. And it actually ends up taking hours, sometimes days of tuning. So I actually had some experiences during my postdoc working with this leg here, an experimental leg built by Vanderbilt University, which performed great. It was excellent when it was well tuned. And so we would bring in a subject and work with them for a couple days, getting it tuned correctly, before we would do a set of scientific experiments or some sort of PR thing showing them walking outside. So days of tuning. So that's clearly not clinically viable. No insurance company is going to pay for that. And so this is the primary reason that we have not seen these robotic legs with powered knee and ankle on the market. There's not a single commercialized multi-joint robotic leg. And so in this talk, I'm going to share some of our work in trying to present a continuous sense of phase for kinematic control of a prosthesis, where we'll have something called a phase variable, which is continuously measuring the progression of the human gait cycle. I'll also talk about our efforts in trying to model a continuum of activities. So imagine walking on any incline or at any speed, any real number, right? Not just a discrete set. And then we'll get into our efforts in trying to actually get away from kinematic-based approaches and instead go towards energetic approaches, which don't depend on any trajectories whatsoever. And the main motivation for this is that when you're wearing an exoskeleton and you have some volitional control, you don't want the exoskeleton to be defining the trajectories for you, right? So we'll be able to do some dynamic volitional motions using this energetic control paradigm. And we'll also talk about the actuators that are required for this type of control as well. So the first effort was to unify the gait cycle under one nonlinear controller using a continuous sense of phase. And so what we're going to do is we're going to define a phase variable, which is going to allow us to have a continuous stance period, which will then switch to a continuous swing period, and so on. But also, we will define a measurable sense of phase that lets us have a unified stride, meaning there's no switching whatsoever within the stride, and it's just periodic and it repeats from stride to stride. And so to define what is a phase variable, I want to first introduce Jesse Grizzle's work. So he was the first person, at least in the legged robotics, from the legged robotics perspective, to use a phase variable to parameterize kinematic trajectories in a time-invariant way. And so the first use of this was on the robot Rabbit, and of course now he has Cassie, and I hear that there may be a Cassie here at some point soon, which is exciting. So the way this works is you need to find a quantity that is part of the system state, which is monotonic with respect to time, during steady walking. So the reason that we need this is because if you can measure that quantity, then you know where you are in time, right? And that way, if you've parameterized your joint angles over that variable, let's say that the time representation looks very similar to the phase representation during steady walking, right? Because the phase variable and time have a nearly linear relationship. But as soon as you have a perturbation, let's say that someone grabs your leg and stops it from moving mid-gait cycle. Well then, if your phase variable stopped progressing also, then your robot would know that it is now phase shifted in the gait cycle, right? It has been held back, and therefore the phase-based representation will recognize that and then just replay the original trajectory, but with the appropriate phase shift. So now we see that there was a time delay here, but in the phase variable representation, if it's an ideal phase shift, you don't see that perturbation whatsoever in that parameterization. And so what this is going to let us do is it's going to let us have a really good sense of control from the human's perspective, where the human can decide to stop walking, right, mid-gait cycle, and the robot will then freeze and match that intended progression. But in order to do that, we need to understand how to measure the progression of human locomotion. So what is a measurable quantity from the human that we can use to control our robot? And so what we have been using is a measurement related to the thigh angle. So it turns out that the thigh angle is sinusoidal for all locomotion activities, right? So your hips are just moving forward and backwards. And that's important for us because sinusoidal signals provide a phase oscillator, a clock, right? So imagine that think of the hip as like a crank to your clock, right? And so the hip is cranking forward your cycle. And so you can measure a phase angle from that. So this is our phase orbit right here, the phase oscillator, and then we can measure the angle of this vector here to tell us where we are in the cycle continuously. And then when the human accelerates, then this oscillation moves faster, and vice versa when the human slows down. So now we have a clock to measure the human's progression. And to verify that this estimate of phase from the hip can be used to estimate the progression of the knee and the ankle, which is what we're controlling for an above-knee amputee, we needed to do a perturbation study to validate this representation. So what we did is we built a perturbation mechanism, which is part of an elevated walkway. And so this is the blue thing is a force plate, so we can measure contact and know when the person strikes the ground there. And then underneath the force plate, which is kind of hard to see, is a 2 kilowatt actuator that can move the stance foot under load about 10 centimeters in 100 milliseconds. Okay? And so imagine if you were to take a step and suddenly your stance foot moved forward or backwards with respect to your center of mass, then you are now forward in the gait cycle. And if it were to move you forward, you're now backward in the gait cycle, right? Because you have to go over that stance foot. Okay, so this is affecting a phase shift. It's not an ideal phase shift, but it's a phase shift of some sort to the gait cycle. And then we're going to observe, using motion capture, how the human responds to that and see if the hip angle is giving us a good parameterization of the knee and the ankle. So we see here a backwards perturbation, which corresponds to a forward shift in phase. And then the opposite is shown as well. And then we time it randomly too. We have different timings so that there's no anticipation. And so what we see here on the left is the temporal parameterization. And we see a shift over time, right? Because the gait cycle has been delayed. And then over phase, we see that shift has been accounted for. It's more noticeable in this example. So here we see a shift. The red is the perturbed, and we see that the gait cycle is now shifted forward, so it's ending faster. But over phase, for the knee and the ankle, you don't really notice that perturbation. Okay, so that means that the hip angle is indeed useful for parameterizing the progression of the knee and the ankle. And this is another way of looking at the data. So first, if you look at, this is the averages of our 10 able-bodied human subjects. So we see that the blue is the nominal case, and we see the backward and the forward perturbations. There's a clear shift over time, right? And when you look at the parameterized kinematics with the phase angle, we see that they overlap very nicely. And in fact, there's a correlation coefficient of greater than 0.99 for the knee. The ankle is not quite as highly correlated, but still pretty highly correlated.
So how does this perturbation in terms of phase differ from, instead of shifting the stance foot, if you kind of push?
Yes. It would be akin to that. I guess it depends on your assumption. So if you're assuming that your foot is fixed, but your center of mass is moving, then it's akin to that, right? It's just that now our center of mass is fixed and our foot is moved, right?
Could you see whether those two different types of experiments give kind of relatively the same effect?
So we haven't tried it. But I think you would see a similar effect. Yeah, but I can't say that with proof. Yeah. And so the star here represents a statistical significance that this is a better parameterization than time. And we also looked at the Cartesian hip position. So that actually may have shown some differences. So the Cartesian hip position is not a good representation of phase for this type of perturbation. Now, if we actually did push the hip, though, it would be interesting to see if that still was true. Right. So yeah.
You can imagine if the time duration of that perturbation were long enough, then the human control system would do something very, very different.
Yeah.
How do you know? Did you test to see whether it sounds like you've got a small enough window that you can see that, but do you know that that's true?
Right. So our intention was to not deviate far from the periodic orbit, so that we wouldn't see some sort of reflex or trip response or something like that, right? Because if you push them enough, they will activate a trip response or slip response, which would be different, from the normal walking motion. So we did some pilot studies to make sure that the perturbation wasn't so big that we were deviating far from the periodic orbit, right? Now, of course, it's not an ideal phase shift, and you can kind of see around here that there is a transient effect. There is. But we do see exponential convergence back to that periodic orbit, which we've not really showing it here, but we have other plots in this paper where we show the effect of the transients. And it's, but actually, we are trying to repeat this study using a instrumented treadmill, which can rapidly accelerate or decelerate. And there, the perturbations tend to be longer in time, but less forceful. But we've noticed it will really trip you up if you don't design the experiment just right. And then you're investigating an entirely different type of control at that point. So, thank you for the question. So this is the take-home message here, is that the hip predicts the timing of the knee and the ankle. I'm not suggesting that it predicts the actual trajectory, but it predicts the timing of the knee and the ankle, which is akin to this notion of proximal controls distal, which is understood in the context of upper extremities. It's been used by Popovic to try to determine intent of grasping, because the shoulder typically moves before the distal joints during a grasping motion. And so they've used that for controlling a prosthetic arm. And now we're trying to extend this to the lower extremities. And another thing that we found, which is kind of a subtlety, but is different than the way that, for example, Jesse Grizzle controls his robots, is that each leg seems to be parameterized by its own angle, right? So as opposed to having one variable controlling both legs. So typically, the walking robots that we see out of Jesse's group are the swing leg is controlled based on the progression of the stance leg. But that's not true of humans, though. So if you perturb the stance leg and not the swing leg will continue doing it'll continue along its original progression until double support, and then they synchronize. Because of course you have to resynchronize at some point. And that happens during double support due to the contact constraints between the two legs. So we found that was a somewhat unexpected observation, because we are not perturbing the swing leg here, only the stance leg, but the swing leg continued along its original progression.
Do you think there's a point at which you're going to apply experiments where that would not be true, and you would still be in this regime where you're more or less tracking your nominal trajectory? Because it seems like that would be a limitation for the human control policy to not adjust.
To not adjust, you're absolutely right. Because, for example, if you need to recover from a trip, you better move your swing leg forward, right?
Pre-tripping, something smaller than tripping, but still the point where you could recover without.
Yeah, I don't know. I mean, honestly, I don't know if there's a stability benefit to this. I'm a little uncertain about that. I don't know if there would be some other small perturbation that would elicit a different response, where the stance leg and the swing leg stay synchronized? I'm not sure. It's a good question.
I mean, is there actually any biological evidence that these kind of two different CPGs?
Yeah, there is. Yeah, so we have tons of decentralization in our biological motor control. And so, yeah, so if you look at these studies of decerebrate cats or spinalized cats, right? They can walk without any information from the forward part of the body, decentralized, right?
No, but that's evidence of could be just evidence of a single CPG that's controlling.
Right.
So you're saying that they're independent CPGs in some sense.
You can think of it that way. I try not to use CPG because then I get myself into trouble. But yeah. Yes, and I think that's also true from these cat studies that they have found that initiation of a single hind limb depends on both loading of the foot and on the hip angle of that single limb. So I do believe that the cat studies support this idea of there being some decentralization between individual limbs. Yeah.
Sorry, it may just be a matter of the net impulse to center of mass being relatively low if you're moving around just the leg.
That's also,
yeah. You don't need to adjust the swing leg so much.
Sure. Yeah, because this is a small perturbation, right? So the center of mass, in fact, we're assuming the center of mass isn't affected. Right? We're assuming the center of mass stays static during the perturbation, and only the stance leg is moving relative to it. So yeah, you're right. So in terms of planting your swing leg, you may not have to adjust your step planning, for example. Yeah. So maybe that'd be interesting to show a perturbation where step adjustment in step length, for example, is necessary. Yeah. Great questions. Thank you. So this is our application to our first gen prosthetic leg. So the idea here is that we have an inertial measurement unit mounted above the knee actuator. So that is measuring the residual limb angle, right? Because the amputee has a socket which is connected to the prosthetic leg, and that it shares the same global orientation as the top of the knee joint, right? It's above the knee joint. And this is a highly geared actuation system, so I just want to warn you about that. It's very rigid, which we have learned a lot from that experience, and now we're going away from that approach, which I'll talk about later. But I just want to point that out. And this is a summary of how we're doing the user synchronization. So we have what we call a volitional control mode, where we have a mapping of just the thigh angle itself. And as long as we know that you're in stance versus swing, you can detect which mapping to use, right? So let's say this angle corresponds to 0%, this angle corresponds to 60%, and as soon as you're in swing, you have this different mapping. And this will be useful for things like just deciding that you want to kick something, right? So as opposed to the phase orbit, which really requires rhythmic, steady motion, because if you stop moving, this orbit will no longer be circular, okay? And so then your polar coordinate here is not going to be working in your favor if you're not walking rhythmically. So we have a switching paradigm between these two senses of phase, but they're all based on the same underlying signal. And by the way, the effect here of we decided to use the integral instead of the velocity for the other axis of this orbit, and that serves both as a filter, and it gives you kind of briefly time-based during these non-monotonic regions. So this hip angle here is not very good as a parameter, as a phase variable when it's non-monotonic. And so during these regions, you can think about it as relying on time through the integrator, and then of course as soon as it's monotonic again, then it's using the time invariance. And so we have to define our trajectories. We use able-bodied human data as a baseline. And of course, we can tune these trajectories. We have a graphical interface for that. But our philosophy is that normative data is a good enough starting point for people to walk. And then we can tune it as necessary. And the idea is you have a function of the phase variable, which is periodic, that defines, because we have two joints we're controlling. We have an output vector, which corresponds to your tracking error from the actual signal theta and your desired, which is h of the phase variable. And then we have, we're using PD control at the moment. We're also trying to investigate nonlinear torque control methods, but for these experiments, we're using PD control. We have 4 PD gains, so 2 for the ankle and 2 for the knee. And so this is a, yeah.
Is there enough uniformity amongst humans that you can get by with the same low parameter H's for everybody?
Yeah.
Parameterization you're using for your H's, that's sort of surprising.
All right, so are you referring to the idea of using an average trajectory for everyone? Is that your concern?
Well, you have some family, and presumably it's got relatively few parameters, so you wouldn't be using it. But then one would think naively that human H's are really, really different.
Yeah. I mean, I'll say this. One of the outcomes of this study was that we were able to have three is not a large number, but 3 different amputee subjects who all use the same trajectories, the same function H, and the same gains, PD gains. So there was no tuning whatsoever between them, which was, again, I'm not saying that was an optimal control system for every person, right? But it was a functional control system for every person. Yeah. And there is also certainly a lot of adaptability that the human has to accommodate maybe something that is suboptimal for them. But you're right. People have variability. People have different walking patterns, but our
Sorry, I guess the question was before you fit on people.
Yeah.
You must have fit these parameterizations to your 10 able-bodied subjects, so you have a larger corpus of data.
Yes, yeah.
Do you still found that a simple low-parameter family would be great for everyone?
It would be good enough for everyone. Yes, yeah. That's what we found. Yeah. So again, we're not trying to predict subject-specific trajectories, or but it's good enough for everyone. I mean, so we're talking plus minus 3 degrees between people typically, and in terms of even our control system can't maintain that type of accuracy. So essentially, especially with the compliant actuator, some of these differences kind of naturally take care of themselves. Yeah. So this shows the concept with an able-bodied person wearing the leg. Okay, so they're able to determine the knee and ankle angles essentially through their hip motion, but of course it is constrained to a walking pattern though at the moment. So this was our first amputee subject when we put the leg on and told him to start playing with it, right? Try to accommodate the leg. Try to learn how it works. And so you can see that he starts this kind of forward-backwards stepping motion, right? And so he's really using the user synchronization to his advantage, and he's learning it. And then we were able to do more types of, and I'm saying volitional control in a kind of a loose sense, right? Of course, the person isn't thinking, I want my knee to be at this angle, but they're able to use the underlying trajectory to their advantage because of the fact that it's synchronized to their timing, right? So this is another example where they can now do step over of obstacles using this user synchronization. And we also have done fun things like kicking balls and let's see. Now, not a great football kick because we don't have the degree of freedom here to actually do a true kick, right? So we only have sagittal plane actuation, and in fact, we don't even have a passive rotation in this way. But our next gen leg will have that. So this demonstrates the ability of the rhythmic control mode to keep up at different speeds. So remember, it's synchronizing to the speed of the human by measuring the rate of the hip angle. So we're able to do walking at variable speeds. And this is essentially the point at which we then need to start thinking about different types of tasks, right? So walking is great, but not all activities of daily living involve walking strictly on a level surface, right? So we could use, again, this hierarchical high-level versus low-level approach where we have a classifier to determine a discrete task for which we have a function h, right? That's one option. But we wanted to try to offer a continuous representation of these different activities as well, if we could. And so this is the approach that we took for dealing with variable speeds and inclines. So the idea is that we're modeling the joint angle as a continuous and separable function of the phase variable phi and the task, which we're calling tau. And in this example, tau is two-dimensional because we're representing speed and incline. But we're also thinking about other types of activities like sit to stand and stairs, which would be separate dimensions of this task. And so the idea is that by modeling it as a separable function, we can use L1 regularization to find a sparse set of bases that explain this large data set that we have for 10 human subjects. Now, we are averaging across human subjects, so we're not yet predicting human-specific kinematics. That is really hard. We've tried, and we have not been successful at it. So I will admit that. But we have been able to find very good models across speeds and inclines. And so in particular, we are able to, for example, leave out an entire walking speed. So say one of these three walking speeds, we leave it out from the training process. But because we have this sparse model, it's fitting to underlying trends as opposed to strictly fitting to data points. And so it's able to predict the untrained activity, which is of course the goal. And we also did this cross-validation study where we randomly generated training sets and validation sets of data, and then we measured the accuracy of the predictions and compared it to just a standard linear interpolation. Yeah?
What's the dimensionality of the basis that you're using?
Okay, so what we're doing here is the bases, we're providing a library of trigonometric polynomials up to degree 10. And so we have hundreds of options, right? And it selects, gosh, I think it's 5 or 6 of them. Yep. And then the coefficients C are a Bernstein basis. So essentially it's akin to a Bezier polynomial, right? Yep. So and so in this cross-validation study, we found that a linear interpolation is pretty good with very structured data, but when you're randomly missing data points, it does a really poor job of prediction. Whereas the low-dimensional representation of our kinematic model is able to predict it much more accurately. And so the goal here is again, we're thinking big. We're not thinking just speeds and inclines, because again, if you have enough samples of speeds and inclines, then your linear interpolation will do just fine. We're thinking trying to eventually get to higher dimensional representations of tasks where we have again, sit to stand and stairs, and maybe even be able to predict behaviors that wouldn't have been trained, right? That we wouldn't have even measured. So for example, sitting to going up a stairs, right? That is a possible transition which we wouldn't reasonably sample that, right? But if we have a good predictive approach to modeling it, we might be able to predict it. And so this is an experiment where we're doing variable incline walking with this model. We are cheating in the sense of we are giving the prosthetic leg the incline angle. We are telling it what the incline angle is. And that's because this is a very rigid actuator, and it's not very good at detecting the slope angle because it's so rigid. So we are working on that problem too. But I just want to let you guys know that we are inputting the slope angle, and then the model figures out the kinematics from that. And then 9 degrees is the max treadmill incline. Okay. And of course, the leg is loud because it's highly geared, has a ball screw transmission. So just keep that in mind because we'll fix that in a second. So this is the result of the amputee study. So we had no parameter tuning across 3 amputee subjects, which is meaningful in itself because it may help with the clinical viability of this type of technology. And we also found that we were able to statistically significantly reduce abnormal compensations compared to the passive usage of the passive prosthetic leg. And our hypothesis for that, for why that happens, is because we are providing normative kinematics and normative kinetics from the powered prosthetic leg. And then the human body no longer has to compensate for the lack of normal kinetics, right, by using the hips or the sound leg. And so we've reduced, there's a compensation called vaulting, which is when your sound leg pushes off early so that you can help clear the ground with your swing leg. So you see this kind of abnormal walking behavior where you're vaulting. We saw a significant reduction in that. And then we also saw the reduction in hip abduction, adduction, which is called circumduction, which is, again, trying to clear the ground with your prosthetic leg. And so we were able to show statistically that that is better with the powered leg. And also we were able to show that, this is not a surprise because our model fits the normative human data. But of course the control was able to track that. And this was more of a, not a surprise, but this was not something that we directly controlled in terms of the work done by the actuators. So we found that by tracking our normative kinematics, the actuators actually did change the work, the power delivery in a biomimetic way for powering the human gait cycle. So essentially, as your speed increases, your ankle work should go up and your knee work should go down. And it did do that, even though we weren't directly controlling for that. The user synchronization and timing and the adjustments in kinematics provided that. And so right now we're working on real-time incline detection. And our plan is to go to more demanding activities such as stair climbing and running. But in order to do that, we need better actuators. And so we are currently working on our own robotic leg, Gen 2, which has low-impedance actuators with a 22-to-1 gear ratio. So we're, of course, motivated by Dan Kodachek's work with the quasi-direct drive approach. And so we're trying to, of course, minimize impact forces during walking, which is important to the comfort, the interaction with the soft tissue of the residual limb. And also, this will allow more compliance to the environment, which is beneficial in many ways. And then we're also working with Elliott Rouse at Michigan on another design approach. This is based on series elastic actuators. Ours is just the quasi-direct drive. And so this shows you the back drivability. So this is powered off. It's not doing force control. And what you're hearing is a compound planetary gear. And so at ICRA, we'll be presenting our paper on this new leg. So you can see it's much quieter than the last leg, right? Much quieter. And we can also, we've designed it for running. And that sound you're hearing is the large force being produced when it is trying to stop its swing period. But of course, there's no hip motion here, right? So the knee actuator is doing everything, whereas during walking, your hip would actually be contributing. So this is actually a very demanding experiment, the benchtop experiment. Normally, you'd have inertia helping you with the swing phase. So the next topic I want to discuss is our efforts in exoskeleton control. And so whereas in prosthetic leg control, we have to produce the kinematics somehow, right? Because there's a missing limb there. There's no limb to do it for you. But in some applications of exoskeletons, we have to augment existing volitional motion, right? So now this is particularly important for stroke patients who have to relearn how to walk. Right? Or perhaps for elderly assist, where they have the ability to move their limbs, but they need help. They need strength to climb their stairs. So the problem, though, is that the current approach to designing and controlling exoskeletons is embracing kind of a rigid paradigm. So this exoskeleton was designed for patients with spinal cord injury, and so it provides all the motion for you, which is totally fine for that patient population. But now we're beginning to see these devices used with stroke patients too, and I'm very doubtful that that's going to have positive outcomes for stroke patients, unless they want to just let the robot do everything for them and not become self-sufficient. So the goal is to provide a control paradigm that is trajectory-free so that it has the benefits of this kind of body weight support training paradigm where you're in the clinic and you're practicing and relearning your leg motions and your muscle control, but it has the mobility of an exoskeleton. That's the goal. And so we are investigating a control approach which is based on this notion of Lagrangian shaping or energy shaping. And so the idea here is that you can define your body dynamics in open loop using a Lagrangian function, which is kinetic energy minus potential energy. And from the Euler-Lagrange equations, you can derive the equations of motion. You have your control input U, and you use that control input to shape your kinetic and your potential energy functions as they appear in your dynamics. And therefore, the idea here is that you're making your mechanical system act like a different mechanical system. But it's still free to behave according to its own dynamics. So, and you can use this to produce autonomous walking gaits for bipeds, which was work that I did with my PhD. And so as long as you shape your kinetic energy and your potential energy just right to provide propulsion and support, then you can actually generate these walking gaits which are dynamically stable without any reference trajectories. Now, of course, the heading angles, I suppose you could think of as a trajectory, but all the joint motion is trajectory-free, just based on passive dynamics. And so no reference trajectories in the context of an exoskeleton would mean more flexibility, more freedom, but it does involve very difficult differential equations in the case of under actuation. When you have fewer actuators than coordinates, then you have to solve differential equations to show the existence of a control law that gets you to the closed loop dynamics you want. And so the take-home message here is that you can't shape your dynamics arbitrarily when you have under actuation. You have to do it within the actuation that you have.
You also need acceleration data, which would be seemingly very daunting.
So actually, you don't in this approach. So the control law.
Change n to n tilde, you absolutely do.
Okay, so what we do is this control law, and forgive me if I'm not answering your question. The control law inverts your M matrix and substitutes the M tilde, right? And so you don't need acceleration to do that.
Oh, you won't add, you'll actually do inverse.
Right, yeah.
Are you where you got inverse?
Okay, yeah. I mean, it's not easy, yeah, and it's subject to modeling inaccuracies and all that stuff, right? So yes, but what we are doing though, our whole idea is that we are trying to, for example, reduce the perceived weight of the person or the perceived inertia of their limbs, and so if we're not doing that exactly accurately, it may still have an assistive effect, even if the net effect is not what we intended it to be, right? And we are also kind of punting the stability problem a little bit to the human. We're saying, human, you can figure out how to stabilize yourself even with these model inaccuracies. But you're right, that it's a challenge. So this is the potential energy shaping part of it. that imagine you have torques at the joints of the orthosis, the knee and the ankle, and you are doing gravity compensation, right? That's essentially what this is. And so you can compensate for gravity regardless of what the activity is that the human is doing. And so it's task invariant. And in the case of total energy shaping, we are trying to reduce the perceived inertia of the limbs. And so the idea here is that through the torques applied to the human body, the human would feel as though their limbs had less inertia, had less weight. And there's also a proof of passivity, which is not a proof of stability in itself, but it lends itself to stabilization. So in particular, what we've shown is that the closed loop system is passive from the human inputs to the joint velocities with the exoskeleton, which means that the exoskeleton can't generate energy on its own. The human is determining the energy growth of the coupled system. So we think that's good because that means the exoskeleton shouldn't have these oscillations or unstable effects as long as the human isn't contributing to an unstable. But then again, that's a big question all on its own. And so we had to design an exoskeleton to accommodate this type of control strategy because, again, this does not produce the kinematic trajectories on its own. We're requiring the human to contribute the kinematics to the walking motion, and so we need the actuators to be back drivable. And so we designed our exoskeleton, which we call COMEX, right? So the Comet's exoskeleton, right? So that was one of our students won a prize for the most clever exoskeleton name. So, yeah. And so we're using frameless motors with a 24-to-1 planetary. 24-to-1 is the overall gear ratio that comes from a belt drive with a planetary gearbox inside the driven sprocket. So that is the net gear ratio, which gives us about 60 Newton meters peak. And so we took off the case for the exoskeleton so you guys could see it actuating. Although it's kind of hard to know what it feels like because there's a person in there. But you can see that he is able to quickly transition from stair ascent to level ground to stair descent, and that's all because this is a trajectory-free controller and back-drivable actuators. And so now we are working on our second generation exoskeleton, which is a slightly different usage. We intended this to be more tailored towards elderly assist. So we're providing less torque, but we're giving them a lighter exoskeleton and a more back-drivable exoskeleton. Because typically, the more exoskeleton you give someone who has their own volitional control, the more it's going to get in the way. That's essentially the typical thought process. And so in order to do this, we designed a custom motor, which uses encapsulated windings to have better thermal conductivity to get the heat away from the windings so that we could overdrive it more. And this motor gives us 4.2 Newton meters peak. We arrived at the radial flux outer rotor after some simulation studies of different type of architectures. This wasn't necessarily the most torque dense option, but it was the most affordable torque dense option. There were more complicated designs that we could have pursued. And then we put the 7-to-1 planetary gear core inside the stator, so it's all very compact. So the motor and the stator, the motor and the gear core are all in one, which gives us this lightweight, compact device, which includes the battery and the microcontroller. And it's about 2 kilograms. So this just demonstrates kind of the way you can walk naturally with this thing. It doesn't slow you down, it doesn't get in the way, but it is providing torque assist at the knee. and it's pretty quiet too. And then our goal is not only assisting people in need of assistance, but also perhaps performance enhancement of able-bodied users, which we don't yet have any evidence to suggest that this does enhance performance, but we're going to start those studies soon. And so this is my last slide, just to share a few other projects that are in the lab or through collaborations without too much detail. I'm working with Kaveh Hamed on some decentralized feedback control approaches akin to this whole idea of the cat locomotion and the limbs being independently controlled. I'm also working with Nick Gans, who's a professor at UT Dallas, and our joint and our postdoc Alireza on real-time model-free optimization of the control gains. And so we're using extremum seeking control for that. And I also have a student, Edgar, who's working on design optimization for series elastic actuators. So the idea there is we have a non-parametric representation of your elastic element of the series elastic actuator. And so we were able to formulate a convex optimization problem for solving for this nonlinear spring, which globally minimizes energy consumption and satisfies actuator constraints, such as never bottoming out your series elastic actuator, because then if you bottom out your series spring, then your soft actuator suddenly becomes a hard actuator. And then for human interaction, that can be bad. And we're also working with the material science group on campus on trying to use dielectric elastomers as variable stiffness units in a series elastic actuator. So these are polymers that when you apply a large electrostatic charge, like 5 kilovolts, they soften. And so that gives you a variable stiffness effect. But they are often used as actuators by themselves, but they don't have enough force output to be useful in a scalable robotic application. So we are using an electric motor to provide the force and the polymer to provide the stiffness modulation. So these are some ongoing projects in a nutshell. And this is my group. I have to thank the students and the staff for their contributions and the funding agencies, the NIH, the NSF, and the Burroughs Wellcome Fund. So thank you very much for your time.
I know we've peppered you throughout with questions, but maybe there's
Yeah, happy to answer more.
some more from the
Yeah.
So, I mean, with all the exoskeletons, right? I mean, what's the best way to kind of evaluate, let's say you have a particular torque reduction model and you do an inverse dynamics.
Yep.
I mean, what's the way to kind of evaluate which ones are actually doing best?
Yeah, so like evaluating the outcomes. Yeah, so one way to do that is to look at metabolic cost of the human. So you have an oxygen mask on, or it's measuring your carbon output, CO2 output, and so you measure how efficient your human subject has become, or inefficient is usually what you observe when you add a device to someone. You can also look at muscle activation patterns. So we have EMG sensors, which we're currently using right now, and we can show that the muscular effort goes down when the exoskeleton is helping. And then we can put it in a reverse mode where it's actually challenging, and you see the muscle activation go way up. So that's kind of a localized measurement, which isn't always correlated to metabolic cost.